So good morning and welcome to the 8th lecture in this course. Today we really are going to talk about the crux of this course. Once you've mastered this, you're at the peak, and it's getting easier from then on. So we have all the tools now to really understand what degrades image resolution in a microscope, and we have covered diffraction. We have learned that lenses perform Fourier transforms, and we've seen that the compound microscope, consisting of a 4F imaging system, essentially performs 2 Fourier transforms. And with that, we can fully describe what happens when we try and project an electric field distribution in the object plane onto the image plane. So with that, I go to my presentation, and I will explain to you the principle of Fourier imaging. So again, if we go back, we said our microscope system just consists of 2 lenses, an objective lens and a tube lens, and information from the sample plane is projected onto the image plane, and we want to do that as faithfully as possible. So this is the essence of Hooke's compound microscope. Nothing has changed really. It's just a technology for us to make better objectives and better detection systems that allow us really to get much better image quality with these standard type microscopes. And of course, we have a much better physical understanding of what limits resolution than what was possible in Hooke's time. So the essence is that you have your object, a focal distance f0 or fo, away from the objective lens, and the information here is relayed onto the Fourier plane of the objective lens. And then essentially what we end up here, we end up with the spectrum, the spatial frequency distributions of the object information, the object field distribution, here in the Fourier plane. And these spectral components are then used by the tube lens, which is again 1 focal distance ft away from this Fourier plane. It is then projected onto the image plane. So essentially, we have 1 Fourier transform going from here to there, and we have another Fourier transform going from there to there. So we have 2 Fourier transforms. So the first step you could think of as a Fourier analysis. We take the information and decompose it into the spectral frequency components, and then in the second step, the tube lens is taking these spectral components and it is synthesizing the image information for us. So it's really quite a wonderful piece of technology if you think about it. So these lenses perform super fast Fourier transforms for you. And so in a 4F imaging system like this, in a microscope system, planes that contain similar information are called conjugate planes. So for example, the object and the image planes are conjugate planes. They're conjugate to one another. On the other hand, the front focal plane, i.e. the object plane of the objective, and the back focal plane of the objective are Fourier planes. So the object plane and this intermediate plane are Fourier planes to one another. And so we have seen already that this system satisfies Fraunhofer conditions. So if we have an object, then what this objective does, it bundles parallel rays of light. So all the spherical waves that can be described going off into all directions. So these spherical waves, parallel rays, are projected to the same point on the Fourier plane. And under those conditions, we have seen we can write the field distribution in the Fourier plane as a integral, as a Kirchhoff integral that looks just like the Fourier transform of the field distribution u of x, y in the object plane. And so we have really got now a diffraction integral that looks like a Fourier transform. And so the objective performs the Fourier transformation of the field distribution in the object plane. Note that I've used the symbol U here instead of E for the electric field. They are the same thing, but people dealing with image formation conventionally use U for historic reasons to signify that the fields represent image information. So just to make that differentiation, and so that you know we're dealing with a field that actually produces an image, we will stick with that convention here. But the physics is the same. We have exactly the same thing. It's exactly the same description as we had previously for E. Okay, so now let's take an example of how this instrument really works. Let's start by illuminating the sample with a plane wave. So when I do this, you can see the plane wave is coming from left to right onto the object plane. The phase is constant across the electric field is completely constant across this dimension here. That's the definition of a plane wave. In other words, all the secondary waves, the secondary wavelets emitted from the object plane, let's take this point here where my laser pointer is situated, that point will emit a spherical wave, and another point along there will emit an identical spherical wave. They're exactly in phase. They are coherent, they're mutually coherent with one another, as we've described. And of course, for this type of imaging, which is called coherent imaging, the fields from these different points can interfere, and we have to take that into account. So we have to work out what is the overall sum of all the fields, and then we square, and then the squaring operation in the end may lead to interference term in the intensity distribution, and that is what actually ultimately leads to contrast. Okay, so let's go on then. This wave travels towards the objective. It's still a plane wave. Now what does the objective do? It now projects the field distribution that I had in the object plane into the Fourier plane. So it's producing the spectrum of this field u of x, y that we had here. What is that? Well, if you have a field distribution that's constant, then we already know its Fourier transform is a delta function. And now you see that that is what the microscope precisely does. The plane wave hitting the objective is now focused down to a point on the Fourier plane. So indeed, the point really just mimics the delta function that we have in the proper Fourier transforms. You can see actually this is a real Fourier transform that you're getting. And so in other words, the spectrum, that's what we are looking at here. The spectrum of the object field has just one component, and that is a DC component, a component at frequency 0. There is no modulation along this direction here, so it just has a DC component present. And so if we now go on, the point in the Fourier plane emits spherical waves just by Huygens again, and the spherical wave is now used by the tube lens and turned back into a plane wave. And so you can see that in the image plane, we have a replica of the field distribution of the object plane. In this coherent imaging case, a plane wave is turned into a plane wave exactly as we require, right? In this particular case. So we have going from this plane, from the object plane to the Fourier plane, we are analyzing the frequency content of the object field. And going from the Fourier plane to the image plane, we are synthesizing the object information from its frequency components. So, of course, when we do this, some frequencies are lost. Can you see why? A plane wave, by definition, has an infinite extent. That's what this means, right? Only a function that is constant from minus infinity to infinity really has a spectrum that's a delta function centered at 0. Of course, the objective aperture is finite. So we can only sample the object plane wave over an extent that is the diameter of the lens. And now you see what happens. So the actual field we are sampling is clipped. And that is what leads to information loss and diffraction. So let's just pretend, first of all, that the objective lens is very, very large. So we have hardly got any diffraction. So putting this into mathematical terms, going from the object plane, we have a field distribution that's constant, plane wave. It is turned in the first operation here it's turned into its spectrum. The spectrum is a delta function, so the Fourier transform is so it's U tilde to denote it's a Fourier transform of this field distribution here, and it now is in frequency components kx, ky. It really has only got one DC component at kx and ky equals 0. And then we perform another Fourier transform with the tube lens, so the spectrum is then turned back into the original field distribution. So a Fourier transform of the spectrum is, as we said before, it's almost the same thing as the inverse Fourier transform. It just differs by this phase term, this minus term, which we don't care about. Obviously, the lens can't do a different operation. Going from here to here and going from here to here, these lenses perform exactly the same operation. They're just two Fourier transforms, but that doesn't really matter at all as far as we're concerned. Because ultimately we still at the end detect intensities when we square things, and then these complex terms, they drop out. Okay, so you have analysis and synthesis. And let's just deal with this problem now of having a finite aperture. So what that does is that the input field is, of course, not infinitely in extent, but rather it is clipped. And so what we really have is, I mean, I'm just exaggerating this here now by actually putting a physical aperture into my object plane, just to make this clear to you. And so for this situation here, this aperture is smaller than the objective lens. So actually the limiting element is this aperture here, rather than what is usually the case in microscopy, the aperture posed by the objective lens. But just to make clear to you what this means. So in actual fact, the plane wave is clipped, so we have a multiplication in real space. The original plane wave, u of x1, y1, is multiplied by an aperture function. In this case, in 1D, that may be a slit function. In 2D, that may be a circular aperture or a square aperture, whatever you like. So so I've just denoted this here with a rectangle function. So you multiply those two things, and then by the convolution theorem, you recognize, of course, that going from here to here is a Fourier transform. So the Fourier transform of a product becomes a convolution of the Fourier transforms of the individual functions. And that's exactly what's happening here. So the Fourier transform of this is just a delta function. So that contains the frequency spectrum of the original field. And the Fourier transform of a rectangle function is a sinc function, as shown here. And of course, so the wider the aperture, the narrower the sinc function, okay? And of course, what we then get is that this point here isn't just a point, but in fact, it is a broad and smeared out point. It is smeared out by this function here. And this function turns out that is called the coherent point spread function. Okay, so the field distribution is affected. So to put this in other words, putting this aperture in affects the spectrum of the input field, of course. And so what we want to do in a microscope is we want to preserve as much object information as possible by making this function here, this what's called the coherent point spread function, we'll get to that in a minute, as small as possible. Okay? All right. So we've dealt here with the problem of a plane wave. So this would apply to bright field imaging. And I would like to say again, this is an example of a coherent imaging technique because all the different points in the object plane are mutually coherent. They all oscillate in phase and interfere. All right, so this brings us now to the next example that is really important for imaging, which is looking at point emitters. Let's look at point emitters in the object plane. So rather than looking at the input field that passes through in bright field image, let's take the more general example, and let's just look at what happens to a point in the object, a resolution element we have. The smallest we can possibly have is an infinitesimally small point. If we could resolve a point and make it as small in the image plane as possible and still faithfully recognize it as a point, then we'd be doing optimally well. There are then two possibilities, right? So in coherent imaging, two different points, like the black one here and the red one shown with the laser pointer, they would oscillate exactly in phase. And so we better end up with something that is going to be the coherent point spread function. We'll look about that. We'll look at that in a second. But you could also have an incoherent imaging technique where all the emitters in the object plane are mutually incoherent. And one super important technique, in fact, the most important microscopy technique for biologists, is fluorescence microscopy. And in fluorescence microscopy, what you do is you excite molecules, dye molecules in your sample. And so one dye molecule may sit here in the object plane, another one may sit there, and they emit spherical waves, these dye molecules, which you capture, and they travel through the microscope just the same as they would in a coherent case. But this molecule knows nothing about the phase of the light field emitted by this molecule down there. So they do not interfere with one another. In fact, what we can do is we can work out what is the field that propagates through. We square that field from that point, and then we take the other point, we let it propagate through, we square the field from that point, and then we add the intensities. The previous point, the other technique, the coherent imaging technique, such as bright field imaging, these 2 points would emit in phase. So we have to do something slightly different. We still work out what is the field that's transmitted through to the image plane for both points, but rather than squaring them individually, we add the amplitudes, because these amplitudes can still interfere, and then square the resultant. And of course, if you look back at the principle of superposition, then if these oscillators are, or if these fields are in phase with one another, they can interfere, you know. And so if they have a fixed phase relationship with one another, then we have to take that into account, and these interference effects then will lead to an intensity distribution that is slightly different than is the case for the incoherent case. And these are really important points because actually you will see that this affects the actual resolution. The resolution is slightly different between a coherent imaging technique and an incoherent imaging technique. But if we just now start by looking at this black point here, whether that's coherent or incoherent, whether there's a dye-molecule emitting light, or whether that's just a secondary wavelet coming from a bright field illumination, is for this part now not important. It's important what we do afterwards with the fields that arrive at the image plane. So here's a point. It has a field distribution that's a delta function now, rather than the plane wave example that we showed beforehand. It emits a spherical wave that is now captured. Well, part of it is captured by the object function, by the objective. It is clipped by the numerical aperture of the objective. And so essentially what we then have is that the frequency spectrum is now clipped. So rather than getting the Fourier transform in the Fourier plane, which would be a plane wave of infinite extent for this emitter here, what we get is we just get a clipped plane wave. So now we are multiplying in the Fourier plane with an aperture function. So we will do that next. So at this point, I just go through the process without the aperture. Initially, I'll put the aperture in the next step. So we're pretending now that actually we get a perfect Fourier transform. So a delta function turns into a plane wave. So its spectrum is a plane wave. And then, of course, the synthesis step is another Fourier transform. It turns it back into a delta function as required. So now what we need to do is we need to actually clip this frequency spectrum here with the aperture function. So we'll do this here. So here we have now in the Fourier plane a product. Spectrum is multiplied by the slit function or by the circular aperture function for the lens. And then we synthesize from this clipped spectrum. And again, by the convolution theorem, we now have the synthesis of an infinite number of frequencies gives us a delta function, and the synthesis of a rectangle function, its Fourier transform is given by a sinc function. So we now have again we have a convolution of a delta function in the image plane with a sinc function, and so what we can say is that the point now is blurred by this function here, and the blurring is essentially a result. The blur is defined by the spectrum of the aperture function that we have in the Fourier plane. In fact, there's an interesting thing now. So what we can see is that we are actually changing the frequency content, right, in this Fourier plane by putting apertures in, by just sampling over a finite extent. We are playing with the frequency content in the original information, right? So you can actually play with frequencies by inserting objects into the Fourier plane. For example, you may say, okay, there's certain frequencies in there that I don't want. So by putting little objects in there, I can remove them. One such example I would like you to think about is the dark field technique, where you insert a pin to remove the illumination light in bright field imaging. You remember the plane illumination wave gets focused to a point, and you just put a pin in there to take that point out. I want you to think about what that does in terms of this Fourier imaging principle. which Fourier components are we playing with when we do that, and what's the result of that? Okay, so this slide here summarizes this in a few equations. So we have now arrived at what is called the coherent point spread function. So the coherent point spread function is related to the field that we have in the image plane from a point emitter. So what is the field distribution that we get in the image plane from a point emitter in the object plane? And so the image is a convolution of the Fourier transform of an aperture function here. So it's a convolution of the Fourier transform of an aperture function, which in this case looks like a sink, with the Fourier transform of the spectrum of the original image information. And the spectrum of a plane wave, the spectrum of a delta function was a plane wave, and its Fourier transform, the Fourier transform of a plane wave, gives you the delta function back. So that's the original point, and it now is broadened out by this function, which is called the coherent point spread function. So for a rectangle, that would be a sink function, and for a circular aperture, that would be a Bessel function. We can also think that we can also think about this in the following way. We can say that the spectrum in the Fourier plane is essentially going back. It's taking the inverse Fourier transform of this. Call it inverse Fourier transform or Fourier transform, doesn't really matter, but the Fourier transform of the sink function turns into the aperture function. So the real aperture function would be, let's say, the opening of the objective lens. So the Fourier transform of the coherent point spread function gives you this function here, and that is times the spectrum of the object, the input object. So for a point, that's what we're looking at. A point has a spectrum that's infinite, and that's now a multiplication, right? So you can see we're just going we can go from there to there, take a Fourier transform, or we can go from here to there, take Fourier transforms, or we can go from there to there, taking two Fourier transforms, and they're all saying the same things. But here we're dealing with frequency space, so these here are frequencies. And here, here we're dealing with real space. So in these conjugate planes, object and image planes are a real space. So this is in real space, and this is in frequency space. So if you think about this aperture here, this aperture function here in the frequency domain, in the Fourier plane, then essentially what this is, it tells you over which bandwidth are you admitting spatial frequencies in the microscope. So over this function here, over the extent of this function, you're letting frequencies pass, and outside the frequencies are clipped. And that's information loss. So this function here is also called the coherent optical transfer function. And in the other one, this function here, the coherent point spread function, that is really just telling you what's the degradation of a point. So if I have a point in the object, how degraded is it in the image plane? Okay, right. So if I just image one point, and I want to get the intensity that I might detect on a detector, then I just square the field at the detector, and what you get is essentially that if I take the square of this function, I get the coherent point spread function squared times the field squared, and that's just the intensity. So that's the input intensity. So we get a convolution of the coherent point spread function, which is squared convolved with the intensity of the with the intensity that comes from, from an infinitely small image of the point. So that's the original information, essentially, the object information, a single point convolved with the coherent point spread function squared. That would be the intensity distribution. The spectrum of this, so again, the spectrum of this is, of course, infinite. It's still a delta function squared is a delta function. So its Fourier transform is still infinite in extent, but interestingly, the Fourier transform of the so the spectrum of essentially of the OTF. The OTF now is the transfer function, this function, times itself. So it's the Fourier transform of the CPSF squared. So Fourier transform of a product is a convolution of the Fourier transforms of the individual functions. And so if you have a rectangle convolved with a rectangle function, what does that give you? It gives you a triangle function. So in intensity space, the spectrum looks different. So this is really interesting. So when I actually take a single point and image it, let's suppose one molecule, I want to image it, then the field that I get is given by this function here. But the intensity is the square, and it is narrower than the field. So it means that actually the point that I image is slightly narrow. It's actually quite a bit narrower than what I had in the field distribution. And this is reflected also in the triangular shape of this optical transfer function. Now you can see that the so-called frequency support extends over the original rectangle. The original rectangle was maybe like this. It goes from -a to a, but now it will go from -2a to +2a. So it's twice, it admits twice as many frequencies. Note also that the shape is different. So some of these higher frequencies are attenuated because of this. And the math brings all this out, right? Because it makes perfect sense from the Fourier transform idea. But so now, crucially, coming back to this point of coherent and incoherent imaging. In the coherent case, you work out the field distribution of each point in the image plane and then square, and that gives you the final resolution. And then you can get interferences between the individual the points, the fields that arrive in the image plane, and actually that then yields, it turns out, to a resolution that is lower than what you get if these points didn't interfere. They don't mingle with one another. In the case of fluorescence imaging, where you have emitters that are unrelated, so this emits phases that are completely uncorrelated with the phases here, they don't know about one another. So what you do is you work out what's the field of this one over there, square it, work out what's the field of this one, and square it, then you just add the intensities, no interference. And the result of that is that you have a transmission of frequencies that is higher. You get more information because these interferences don't take place. It sounds complicated, but if you work through this in your own time, this will become obvious to you. Right. So you can now see what happens. So if I look at the microscope, I'll just say it's a black box with a certain aperture A. I have a point in the object. It now turns into a blurred point in the object plane. And so the field distribution would be the coherent point spread function. Its intensity, if I just look at that point, will be the point spread function, the coherent point spread function squared. And so if we just deal with the intensities independently and use the coherent point spread function squared, then we get a narrow peak. And typically the the width of the peak that we get is given by lambda over 2Na. It's proportional to the width of the aperture. So that would be for the incoherent case, lambda over 2Na, and for the coherent case, it's lambda over Na. I'll come back to that in a minute. So typically, if you have visible light, green light, this can be of the order of lambda over 2, and this may be of the order of 240 nanometers if you have a very, very good lens. The other way to think about this, so this is thinking about painting out the picture. Each point here is if you have a picture in the object plane, then you're painting that with a function a pencil that has the shape of the point spread function, essentially. And the other way to think about it is about the optical transfer function. You can just say, okay, looking in the Fourier plane, which frequencies pass? And of course, the aperture, the finite aperture here means that higher frequencies higher than a certain limit cannot pass. And that's governed by this numerical aperture, of course. So that's what PSF versus OTF mean. And so I just wanted to go back. So for fluorescence imaging, where this will become most important for us, so for all the high resolution imaging techniques, we deal with incoherent point spread functions. They're much more important to us. Most of the techniques, unless we use bright field imaging, most of the techniques are incoherent imaging techniques. And so we just take the coherent point spread function squared and then add up the intensities in the image plane. And so we just call that the so-called incoherent point spread function, we just call it PSF, the PSF, and the corresponding frequency support is called the optical transfer function. Okay, so the imaging operation is now clear. If you have a couple of points in the object, let's say different dye molecules. The dye molecules, let's say these are incoherent emitters. Each molecule will be mapped onto a Bessel function squared, right? So that would be the PSF. The Bessel function squared would be the PSF for each molecule. And so you get a bunch of PSFs sitting next to each other. And of course, when the PSFs have a certain width, as soon as they get and start overlapping significantly with one another, you cannot distinguish these points from one another. So you can see now what I mean. Imaging is a convolution operation by way of the fact that the two lenses perform two Fourier transforms. And with that, I finish this part of the lecture. And in the next video, what I will do is I will talk you through the theory of coherent imaging and derive and give you an idea of why really the resolution is lower in coherent imaging. And the theory behind this is by Abe, and it's wonderful because it actually incorporates all the bits that we already know, all the tools. And so I hope I'll be able to make that clear to you, and look forward to seeing you in the next bit. Thank you.